Thank you. Well, first of all, thank you so much, Tapiwa. I really enjoyed that. I think sort of the holes come either because people haven't learned it or because they've learned it, but there's so much jiggling about that then you forget something along the way in a little corner of the website. So it's always really good to have this kind of reality check, and it's a really great overview. So thank you. And I am particularly happy to be in a joint meetup from South Africa and Wales, because these are two places that I feel a sort of a strong connection with Wales, because actually this was one of my very first meetups ever, PHP South Wales, sorry. It was the second talk I think I gave, and I became a British citizen in Wales. So I think I can say I am legally Welsh, even though I am in every other way a Mexican. And so it's a lovely thing to be there. And then I have such love for Africa. And I know that sort of in Mexico, there's things that make us kind of unique, but also there's a spirit to Latin America more generally that we share. And I spent sort of serious time in Kenya and Uganda and Tanzania in the east and Sierra Leone in the west, Morocco in the north, and I've never yet made it to South Africa. And I've wanted to. I had the great privilege to briefly be face to face with Nelson Mandela. And that brief encounter stayed with me. It actually was impressive and impactful. And so being in this meetup is like shortening the distance. I'm getting closer to visiting you there one day and sort of drinking in the spirit. So thank you so much for organizing this. It's a wonderful thing and for having me on. My talk is really complementary because the previous talk, Tapiwa covered the application layer, and by then you're already in. Whereas what I'm going to talk about is the network layer, the IP side of things. And it is called a blagger's guide because I'm blagging it. Blagging it is when you don't really know the subject thoroughly. So you learn to talk about it. And in this sense, I am not a network admin. I am not an expert in this area, but certainly as a web developer, a lot of this stuff that is integral to everything we do was quite mystifying to me. I was like, give me an application, but don't talk to me about networks. Don't talk to me about CIDR and IPs. And by the way, most people pronounce it CIDR. And a few people pronounce it CIDR. So I have to remember to say CIDR to be with the big crowd and not the small crowd. But yes, so this is in a sense sharing what demystified it for me in the hope that it will help demystify it for others and a particular sort of implementation of one of these aspects. So I hope it will be of value or interest. And if somebody knows a lot more than I do, which they probably do, then they will surely add their knowledge at the end. So hello, my name is Ismael Velasco. I am a Mexican cosmopolite living in Wales until 3 weeks ago. I just moved to a part of England called Suffolk. I am a PHP developer and a circus trapeze artist. Only one of them is true, and I'm really hoping that by the end of the talk, you believe it's PHP developer and not circus trapeze artist. You can find me on Twitter at Dev on a Journey. I have found Twitter to be a wonderful dev community. This account is just for my dev interactions and conversations, and I don't experience any of the toxicity that is famous in Twitter. All I get is cutting edge news on sort of stuff I care about, lovely people, good insights. So if you are active on Twitter in the conversation, please join me, reach out. It would be lovely to be in touch. So let's begin with some key terms. IP, Internet Protocol. It is, I would call it the Internet's postal system. It has the task of delivering packets of information from the source host, which is to say machine or device, to the destination host solely based on IP addresses in the packet headers. So it is exactly as the postal system has the task of delivering letters from one postal address to another postal address. And the IP routing equals the internet. If you think about it, if you add all of the addresses in Britain or all of the addresses in South Africa, that, you know, on the one hand, there's the land, and that is South Africa, and that is Britain. And on the other, there's all the people that live in it, in all of those addresses. So IP routing, the collection of all the routes, in a sense, is the internet, is the map of all the connections between all the machines in the world. So now let's explore an IP address. IP addresses are of two kinds, IP version 4 and IP version 6. So IP version 4 is made up of 32 binary bits, as it's a unique identifier for a device on an IP network. This is the one that most of us see and know, the numbers, like the one that somebody posted in chat of 255.255.0.0. It's the keywords there are 32 binary and bit. So binary means ones and zeros, and 32 bits means 32 ones and zeros. So every IP address in this implementation is a series of 32 ones and zeros. But for human readability, we convert this 1 and 0 into decimal, and therefore go, instead of 10101010 32 times, we end up with 255.255.0.0. So we'll explore this in more detail in a second. 64% of internet traffic happens through Ipv4 addresses. But there's a problem. There's a scarce availability. When you create the address, you get 4.3 billion unique IDs, which sounds like a lot, but it's actually very little compared to the amount of devices that are connecting to the internet. So it's all the computers, all the mobile phones, all the fridges, all the door locks, every single device that connects to the internet needs an IP address, and there's only 4.3 billion. So they've actually now been fully allocated or reserved. I think 2019, Europe was the last region to allocate its last IP addresses, which means that they've gone. In fact, a lot of people have extras. They bought many IP addresses that they're not using, particularly large organizations. And so they will lease them out, for example, or if they have moved to IPv6, they might consider a number of them redundant and they will sell them. And also, obviously, sites come and go, devices come and go, so IP addresses disappear and come back, and so they get recycled as well. But essentially, it's called IP exhaustion. We are at a point of exhausting our addresses. And it is quite a cheap implementation, and it is the default. All of the hardware in the world speaks IPv4. Then you have IPv6. This is a 128-bit address. So that is much larger. That's 128 ones and zeros. So it's a much, much bigger. And it's been rising gradually, and it's reached now 36% of internet traffic. It is better than IPv4. It has enhanced features, it's better for security, and it contains 340 trillion unique IDs. So you're not actually going to be running out of IPv6. So why is it that only 36% of the internet is moving into IPv6 when we've known this is happening since 1998? The reason is that it's actually quite expensive to implement IPv6, and a lot of hardware is incompatible. And most providers who offer IPv6 also offer IPv4 for kind of backward compatibility. So there isn't such a pain point that is driving people to leave IPv4, nor such reliability of access, universality of access of standards, that you can just go to IPv6 and know that you'll be able to talk to everybody. And there have been a number of workarounds around this exhaustion, one of which is CIDR. But others are things like I mentioned, the recycling of addresses, the leasing of addresses, the selling of addresses. All of these things together have meant that we're kind of coping so far. And so in reality, although IPv6 is much better and really important, and IPv4 is scarce and it's pressured, we are miles away from moving to IPv6 as a standard. IPv4 is our reality for quite a long time to come. So what is an IP network? An IP network is a group of devices connected via their unique IP addresses. So a local area network, an intranet, and the whole internet. So if you think of it, you could think of Britain as a group of homes connected by a postal system. And you could think of a neighborhood as also a group of homes connected by a postal system, but in a smaller scale. And you can think of a street in the same way. So similarly, you can have networks of different scales, and all the devices that connect in that network are an IP network. They divide into subnets, which allow data to travel shorter distances to reach its destination. So the metaphor here would be, imagine that you want to send a letter to someone 5 doors away from you. If you have to drive to the nearest city to put it in a postbook that then will be taken to a central depot, that then will be sorted somewhere else and finally posted right next to you, that's going to take a lot longer than if someone can just take it 3 streets along. So you create subnets that are like IP neighborhoods. So instead of going, send this to Britain, England, Suffolk, Occult, house number, you would just say, send it to 55. And you would know that you don't have to go all the way through all of that process. You just send it straight to the site. And finally, subnet masks designate the part of the IP address devoted to the network as opposed to hosts. So as we will see in a second, an IP address has 2 parts, and one part tells you what is the network. It's like the address that says, this is the street. And one part tells you what is the host or the machine, which is the equivalent of the street number, so to speak. So let's look at an IPv4 address. 150.0.0.0. This is a pretty average IP address. As I mentioned earlier, it has 2 parts. One part is the host machine, and the other part is the network. In the sort of first implementation on IPv4, you had what is called a class-based implementation. So a C-class IP says all of this is the IP address, A, B, and C. And only the last numbers are the host machines, which means that you can only have 254 machines. We'll explore it in a second in more detail. Now, if you do it here, if you have a class B, then your network address is this block and this block, and then these 2 are for individual machines. So you can have 65,000 machines, and so on and so forth. If you are in an A class, then all of these are machines. So it's a network with a huge number of machines, gigantic, and this is your network. So let's now understand how this works. I mentioned that there were 32 bits. So each of these bits is broken into, these are 32 bits. And as you can see, it's got 4 sections. So each section is called an octet. And it's called an octet because each section has 8 bytes, 8 bits. 8, 8, 8, 8 make 32 bits. So your IP address is a 32-bit binary address. divided into 4 sets of 8 binary bits. So here you have the 8 bits. And the way you convert binary to decimal is that the rightmost position has the least value and the leftmost position has the most value. This is the least significant bit. This is the most significant bit. So here we have 2 to the power of 0, which mathematicians will tell you is always 1. Then to the power of 1, which is 2. So you can see that the value of each of these slots doubles each time exponentially. So 1, 2, 4, 8, 16, 32, 64, 128. If you add these 8 bits, you get to 255. So that means that no octet can be higher than 255, because if you went higher than 255, you would need more than 32 bits. Or more than 8 bits, I should say. So each octet has a 0 or a 1 and aggregates into a value of between 0 and 255. So you could have 0.0 all the way to 0.255, 0.0 all the way to 2.55, and so on and so forth for each of those. Now let's look at this particular one. It's 150, 0, 0, 0. So in the first instance, you have a 0, which gives you, I should say, in this case, this one has a value of 0, which means that all of the 8 bits would be 0, right? They have no value. So 0 always evaluates to 0. No matter in which position you put it, it will always have 0 value. So if you see a 0, it means that all of the bits are set to 0. 0, 0, 0, 0, 0. And here, when you get to the A, you know that there's going to be some 1s here. Here, there are no 1s. Everything is 0, but here you'll have some 1s. So how do you get to 150 in the last octet, the last set of 8? So the first bit is 0. Sorry, it doesn't correspond with this. 0 has a value of 0. 1 has a value of 2. 1 has a value of 4. This one has a value of 0. This one has a value of 16, 0, 0, and 128. If you add 2 plus 4 is 6, plus 16 is 22, plus 128 is 150. So this is how you get to 150. This is the decimal equivalent of 100101110. So the whole 32-bit address would be 100101000000000, and the same for the remaining 2. And therefore, this is the most significant bit because it's worth 128 points, and this is the least significant bit because it's only worth 1 point, if this was a game. So now from IP address to CIDR blocks, why would you then go to a CIDR block or a CIDR block? I'm going to use both sounds and then everybody will be happy. So class A, remember that's just the first octet is for the network address, and all the other octets are for individual machines, for host identifiers. So if you only use the first octet for the network and all the other numbers for the others are an individual machine, you can have as many as 16 million machines. So a class A IP address will have 1 octet, the first 3 numbers, decimal numbers for the network, and all the others will be individual machines. A class B one will devote the first 2 octets to the network, so it will only have 2 octets left, the last 2 decimals, as it were, in the decimal IP address. And that gives you 65,535 hosts. And finally, in the class C, all of the address is for the network, and only the last one gives you the host identifiers, which evaluates to 254 host identifiers. Now, if you're a company, and you have 30 computers or 40 or 50, you would go for a class C, and you would now have 204 redundant machines. So you can add another 204 machines, and your 50 machines have each one of the addresses here. Now, what happens if your company has 257 machines on its network? You're going to have to buy a B class address and have 65,300 and something machines, host identifiers that you're not going to use, just so you can go above your 254. If we had 3 trillion identifiers, sure, maybe you could be that wasteful, but in the current climate, that is ridiculous. It is ridiculous and expensive for you to have space for that 65,000 devices when you only need 257, but that's it, you've gone past the C. So what this means is that that network subnet address, the way that is a fixed one, it's not variable, right? You have 3 lengths of the subnet. The subnet is, as I say, the bit that you allocate to the network. So you only have these 3 choices of length, and that's it. And this is where CIDR notation came. CIDR uses variable length subnet masking to define prefixes of arbitrary lengths, which are much more efficient than classes. Now that, if you've not looked at this, is gobbledygook. So what this is saying is that instead of just having 3 choices of how much of your network you subnet and dedicate to the network and how many you free for hosts, and just having these 3 choices, CIDR allows you to have a variable length that is much more precise. So you can now have any arbitrary length to only get your 257 machines and a few others, and not have to go for 65,000. The network address is written as a prefix, like a normal IP address, 192.255.255.255, for example. And the second part is the suffix, which indicates how many bits are in the subnetwork. The 12, the subnet mask. This is the bit that makes it a CIDR address. You do 192.255.255.255, and then you add the 12. And what does that mean? So in this example, let's look at this. So we are saying that we're going to dedicate 12 bits to the address, to the subnet, so to the network address. So that tells you what? That the first 8, so the first octet is fully occupied. That means that you're going to keep 192. 192 will be part of your network address because you're going above 8. So all of the first 8 bits are occupied by the network. And then you have 4 left. That's 12 left. So that means that half of the, that's 4 left out of 8. So half of these bits will be now dedicated to the network, and all the rest from here all the way to here will be individual hosts, will be IP addresses. So you've got the first host is 1.92.240. How do we get there? So 192 we get, why? Because we've said we're occupying the first 8 bits. So all of these are occupied. So we're keeping these 8. But now we have to take away 4 bits from the 8 bits that compose this second octet. So if we look at that, then your 4 bits, because the first 4 bits are taken, all this would be taken. Now, if we add these, 1 plus 2 plus 4 plus 18 is 15. So you take out of 255 15, and you say anything below 240 is part of the network. So you think it's only from 240 onward that you've got IP addresses. which means that your last host IP is 255.255.255. What does that mean? It means that you can fill all the bits essentially, right? You can go from a minimum of having zeros. So if you have zeros in the remaining ones, then you have 192.240, or you could have ones. And if you cover all of them in ones, everything that remains in ones, you would have 255 in the last octet, 255 in the last octet. So all of the IP addresses between 240 and 255.255.255 are now your host machines, which gets you to 1,048,576 hosts. You can see that this is somewhere in between these two. This is obviously a really big network. This might be, I don't know, an ISP or a massive company that's invested in all of that for redundancy. So, yes, what CIDR does is allow you to use the very limited IPv4 space in a very granular way. So you're only consuming the IP unique identifiers that you need for your machines and not paying for stuff that you don't need, nor hogging the space that others might want. So it's actually a really clever and useful thing. The other advantage of the CIDR notation is that it allows you to refer to in this case, if I wanted to list all of these IPs, I would have to write 1,048,576,000 entries. If I wanted to say, for example, I don't want any traffic from this range, I don't want anyone from this range, or maybe more realistically, I only want people from my network, so only from this range. If I didn't have CIDR notation, I would have to write every single IP, and that's obviously silly. But by using this notation, I can already tell my system that I want to engage with the 1,048,576,000 IPs that are contained in this CIDR range. So it's not just about the kind of maximizing of the space, but also about what you can do with CIDR ranges in terms of your network programming and security. So now we've got those covered, let's look at the IP access risks. The Internet Protocol is the basis of device-to-device communication. If your network is open to all IP addresses, it provides a huge attack surface for malicious devices to talk to your machines, like keyloggers or malware or brute force attacks, impersonation, etc. So in the case that Tapio was talking about, for example, this is an app that is open to the world. And that's why you have a login screen, right? You say, everybody can come and now log into me. And then you go, okay, now I'm only going to let you in if you can prove you are who you say you are. But once you got there, that means that that login page could be bombarded by sort of bots, by brute force attacks, by all kinds of things. It also means that, for example, you might have ways of sort of somebody has already compromised, somebody leaked your credentials. So now they just need to go to that login page and they put the correct credentials and they identify themselves correctly and they're through if you don't have MFA, multi-factor authentication in this example. But the point is that by making your network open to every IP address, you are inviting a lot of attacks. Your surface is huge. So restricting IP access to your network can reduce that attack surface and prevent or mitigate attacks. And this can be done through access control lists. So if you're saying only the machines that I trust as designated by their unique IP identifier can come in, then that means that others don't get that. One approach to restricting IP access is to ban only IP addresses in a deny or restriction list. This is what was traditionally known as a blacklist, but its more progressive side of tech has embraced the recognition that the language of blacklists and whitelists is loaded. And although there is silly debates as to the etymology of it and whether it's associated to race or not, what is not under debate is that the connotations, the current connotations of blacklist and whitelist are hurtful to significant proportions of the world. And so since it doesn't cost anything to just call it something that won't be offensive, a lot of massive tech organizations and companies have mothballed the terms whitelist and blacklist and replaced them with deny restriction lists for blacklists and allow an access list for whitelists. So I am very happy to be part of that process of inclusion. So one approach then is to create a denial restriction list. You say any IP address that I don't like cannot get in. I'm going to list all the, someone put a naughty and nice list. So this is the naughty list, right? Anyone who's in the naughty list can't get in. This is convenient, but risky and inefficient. Another approach is the opposite, to just go hardcore and ban everyone. No one can get in. Absolutely no one can get in except the few people who are in my nice list. Only you and you can get in and nobody else can come here. I don't care about your credentials. You don't even have to, you can't even begin to tell me who you are. You're not coming in. This can be better, but it's also trickier and has some gotchas. So what are some pros and cons of the denialist approach, the naughty list? So pros, it is simple and logical. You detect a suspicious or malicious IP, you block it. One company I was part of, for example, had a lot of attacks from China and no clients in China. So they created a blacklist that simply said any IP from China is now in the naughty list. It's harsh, I know, but since actually nobody is our client in China, then nobody has any reason to be visiting us, and the people who are visiting us are trying to attack us. So this is one use. It can be good for spam. There are, for example, really well-known sites that have embedded malware. So if you have those lists, then they get blocked. There are IP addresses that if you use a mail service, then you might be on a shared IP and the person next to you is massively spamming people. And so your IP address may end up in a blacklist and suddenly your emails are not getting through. So it's got good things, but as you can see, there can be some cons. So first of all, someone can just change their IP address. If it wasn't geographical, if it was, this person or this site is doing something, now let me just put this app in or this IP address in my block list, and then someone or an algorithm goes, oh yeah, you blocked me, now I'm just going to change my IP address. And suddenly they're not on your IP address, you've only delayed them if it's a machine for a few nanoseconds. It's also possible to spoof addresses. So you could pretend to be coming from another IP and your naughty list no longer works. Botnets, if you're being attacked by tens of thousands of IP addresses, then it's not realistic to be listing all of them and blacklisting them, especially if they're transient and temporary. You can get false positives. You end up banning an IP address that wasn't, or inaccurate IP detection, because the way one of the hacks that we've created to deal with a very limited number of IP addresses is to have something called an AT, and I'm not going to go into it, but essentially you are translating your local address into a public IP address that could be used by several people. So you are essentially having the same IP address in coming from different people. So you're banning the individual that you want to ban, but you may also be banning another few individuals who you do not want to ban. So it is good. It has its uses, but it's a very blunt instrument and full of holes. It's a good thing to have as part of your security strategy, but not remotely rely on it. Much more powerful is the allow list. Any attempt to connect to your environment will be blocked without being given the opportunity to even present a username or password, unless the connection was initiated from the authorized network. Suddenly, you've actually cut away a huge proportion of attacks. You don't have to worry about spammers. You don't have to worry about any of that stuff. You know that the people who can attack you has been cut by exponential proportions. So this is really much, much, much safer. It prevents potential brute force attacks, reconnaissance of your environment, and exploitation of vulnerable solutions from anywhere else on the internet. So some of the examples that Tapiwa shared, for example, of stealing cookies, etc., none of this would apply, because if you're coming from the wrong IP address, you just don't get in. The application layer is safe, it's not touched. It also has a con. If you do that, as one example, you will limit access for remote workers. So if you say only the IP of my corporate network can get in, then the moment that I start working away from home, I can't get in. So then you might, for example, invest in a virtual private network, and then you say, I won't accept anyone from outside of my corporate network except one IP address, which is the VPN. And so if all my remote workers log into the same VPN, and once they're in the VPN, they have the one IP address that I like. So there's only one nice address in the allow list, and no one else gets in. This sounds lovely, but it has gotchas that may require more complex security measures to mitigate. Now, some gotchas, for example, is that if you use a VPN, you now have centralized access. So although the attack surface is much, much, much less, if someone does break through your VPN, they now have access to all your resources, physical and cloud-based. So having a VPN is not the same as working in an office premise. In an office premise, you can, if something goes wrong, you can say, hey, who's here? And if you see someone who you didn't hire, you can go, it's probably you. In a if you are coming from a VPN, then it could be anyone. And now I am in the nice list. And not just me, but me and all my friends, right? Anyone who can get through. So this means that we need extra layers for authentication and isolation for sensitive resources. Someone just said, never trust anything local or not. And that is true. So actually, even if you do this sort of IP address and you say, okay, only from my network, actually, you still need to add other layers. You need to have layers that are not accessible via your whitelisted IP address. You need to have additional two-factor, ideally multi-factor authentication, which is something I have, something I am, and something I know. So, if I have to confirm that I'm me by something in a device that I own, that's harder, right? And also answer a question about who I am, and also sort of give something of what I know, then that's more secure. So your access list, your allow list, might basically be the first line of defense that says, okay, you are now allowed to face the test of authentication, as opposed to you are allowed in. And you might do ingress filtering. You might inspect once you've said, okay, you look okay, you've got the right numbers, come in. Now I'm going to inspect more closely, not just what you're saying is your sort of return address, so to speak, in your envelope, but also to actually see what is your address of origin, because maybe your address of origin, you're pretending to be coming from a place that I know, but actually your place of origin is in my local network, and something is wrong there. So IP restrictions are very powerful and useful, but they should never be the only line of defense. Having said that, I will now sort of explore how you implement an allow list using CIDR validation. So this is the code that I've used to validate CIDR ranges. So why, first of all, use a CIDR address instead of IP address? Well, I think by now it's pretty clear. If I want to whitelist, so to speak, as people used to say, if I want to allow only sort of an entire range of IP addresses, and I don't want to be typing them one by hand, and I also know that their IP addresses might change because they're not static, but they will be within a network. They will be within a range. So they're not going to be away from the network. They'll stay within the network, but they might not be constant. So I can't predict whether the IP address will be 0.255 or 0.040, but I can predict that it will come from 150.0.0, for example. So, so a CIDR block allows me to say, allow all of the addresses in bulk in one line from all of these, from this network. I'm saying whatever comes from this trusted network, all the individual IP addresses that belong to this subnet, to this network, are allowed into the next stage of validation and security. Now, when someone enters how does that happen? So the way I implemented it, and we implemented in my company, was to create a basic form where the user, so our use cases that we've got lots of companies who use our service, and they each have their own private networks. So they require that our app restricts access to only their network for their client. So we need to have a way of listing what those IP addresses are. And that could take quite a lot of time from our DevOps team in sort of adding all of these things to our allow listing configuration. So we created an app that allows us to input those CIDR ranges and have them, through the magic of PHP and Ansible and other stuff, become a barrier. So in order to do this, we needed form validation, so that when you write a CIDR address, you would not put the wrong CIDR address or a malformed one. So the validation that I used, one was to cheat by not reinventing the wheel. And having inspected a range of options, we went for a package called Node CIDR. And there are, in some ways, better packages. Node CIDR has certain limitations. First of all, it's no longer particularly maintained, but it is self-contained. It has no dependencies, so that's not a problem. It's not going to break, and what it's doing is pretty constant. And if we do need to change it, we can fork and change it, because it does something very narrow and very specific. So that's how we mitigate. But there are libraries that are sort of updated currently all the time. The second limitation is that Node CIDR does not deal with the validation of IPv6 addresses. But we concluded that actually IPv6 is not really practical at the moment. It's not a real world scenario for us, where people will actually be trying. Everyone who has IPv6 also has IPv4, and most people don't have IPv6 but do have IPv4. So by supporting IPv4, we actually don't exclude anybody in a way that we would if we had IPv6, and there is no reason to duplicate both. So that wasn't a pain point for us, but if you do want to support it, then again, there are other libraries out there. What Node CIDR did have that other libraries did not have were fantastic, very granular validation messages. So other sort of more popular apps or libraries would give you things like your CIDR notation is wrong, and maybe a little more. But we will see that Node CIDR gives you really granular, you are missing an octet. This would be better, you put 0.1.1.1 in a CIDR notation where really it would make more sense for you to do 0000, unless you're doing a 32 at the end. So we'll explore that in a second. So Node CIDR powers a lot of the validation in the form. However, we need to add external or additional validation to just sort of whether it's formally correct. Someone said, don't trust anything, including local. And indeed, one of the ways you do ingress filtering is precisely by checking that you are not allowing reserved ranges or local ranges, or I forget for a second the name. There's a name for fake ranges that you could put bosons like sound. It's not that, but it's got a fun sci-fi sounding name. But the point is that someone could invent an IP address to make it work, so to speak, to hide where they're actually coming from. So we decided to add some extra validation. In addition, we also didn't want to, open up a CIDR range of 8, because as we saw, that would give you millions of IP addresses. And none of our clients will have millions of machines. We're not working with an ISP or something like that. So it made sense to put the sort of the bar start at 16, which is already huge. So that means that if you've got, loads and loads, I can't remember how many there are, you can still, be allowed. So our CIDR ranges begin at 16 and then at 32, because you cannot actually have an IP address above 32, because that's the 32 bits, isn't it? And there's only 32 bits to an IP address. In addition, there are what are called reserved IP ranges. So link local, there are RFCs that say which ranges should be used for private networks, so you shouldn't use those. Multicast versus single cast, the loopback range, which is a range for testing that your machine can network to itself. And so that local is 1.27, 0.0.0.1 it tends to be, because it's the first one in that range. So we don't want that one. We don't want to allow that one in. And we have the broadcast range. So all of these are different types of ranges that the rulers that be, as it were, the people in charge of the standards of RFC have reserved. They say this should not be used by people. And thus, when people are connecting outside of their network to our app, they should not be coming from all of this. So in addition to checking whether or not the IP range that someone is inputting to whitelist is valid, we are also checking that it's also not reserved, and we're also checking that it is not monstrously large. So how do we do this? So this is JavaScript, and we're saying V is the value, is CIDR is the name of the function, and so if there is no value, return true. This is just so that the form does not give you an error if it is blank. So if you haven't inputted an address, like you're adding another one, and the validation detects that it's empty, it goes, okay, go ahead. Then you have the next layer. Okay, now somebody has inputted a CIDR value. Let's now validate it. And we put in the value. CIDR.validate is using our library, CIDR, and the method, which is Node CIDR, and the method of the library called validate. So this is the bit that matches whatever the user inputs against all the rules that make a CIDR address correct. So if it finds something, then it will issue the library error. If it doesn't have a library error, then it means that it is valid as an address. So now we need to check that it's also acceptable to our use cases. So first of all, is it in our range? Is it over 62 and below 32 bits? And if it isn't, then message us and tell us that actually you've got the wrong number, the wrong subnet mask. And if it is within range, now check that it is not excluded, that it doesn't belong to the reserved CIDR addresses that we don't want. The other thing we're checking is that the description that we will add for each CIDR is not exceedingly long. And now we check that it is not excluded. Now, originally, when I didn't really know much about this, I actually checked against the array of all the IP ranges. And I didn't realize that some of these ranges are millions of entries long. So it was very, very slow. So using the library of Node CIDR, we are turning the IP address into an int value. And then we are checking that each of these ranges, there is a method that gives you the first and the last IP address in any of these ranges. So rather than give me a million IP addresses, it says the IP address begins, like in the previous example, in 150.240.000 and ends in 150.240.245.255.255. So I'm only getting the first and the last. So I'm saying that the range is from the first IP address to the second IP address. And then I am doing a switch where if I recognize it, if the IP address that somebody in check excluded, the CIDR address that somebody put in does not fall in between the first and the last of the IP values, then of each of those. So if it does, then you recognize it, right? If the IP address in the CIDR range is one of the ones within the link local range, then tell us that that is the case. And so by the end of it, we've checked that the CIDR address does not fall between the first and the last of each of those ranges. And finally, if it doesn't fall between the first and the last of each of those, then it allows us to proceed. So what does this actually look like? I work for a company called BibSync. BibSync has been a very disruptive and successful app in the knowledge management space within fintech, within particularly investors, asset managers, venture capital, really, really, really big endowments, fund managers, etc. They're processing a huge amount of information, a huge amount of information to make investment decisions. And they are also under very, very strict compliance regimes that require very, very high security protocols. And usually the alternative products before BibSync came along involved a kind of compromise on one or the other. You were either compliant or you were very functional. And what BibSync's kind of unique selling point was to create an app that allowed you to have really powerful knowledge management, aggregating every possible data that is coming to you to make informed decisions in clever ways, whilst at the same time managing that data in ways that were fully secure and compliant with the very complicated compliance frameworks in the finance sector. And clearly enforcing CIDR allow lists is part of that compliance. And this was simply a helper tool to make it faster. And the product that we have functions as a web app, as a mobile app. We have data insights and visualization ones, obviously client admins and reports and a desktop app, APIs, etc. So the idea is to have a very fine-grained approach to whitelisting. Some of these you might want unrestricted. You want anyone to be able to connect to them. And some of them you might want restricted. Nobody can connect to them from outside. And others you might want restricted to only a few IP addresses. So in this case, we kind of choose, and this tells you the status. This one is restricted to permitted IP ranges, and this is unrestricted IP access. So if we then choose an app, we have the instructions that they must be an Ipv4 address in a range between 16 and 32, all of the validation that I mentioned. The changes may take 5 minutes to propagate, and when that was last modified for logging. So now we say, actually, I want to restrict, I want to deny access to all IP addresses, not in the IP access list. This again reminds me that the status is that it is unrestricted. So if I then choose to deny it, it is now restricted to only IP accesses within the access list, and the maximum time for it to propagate is 5 minutes. So this is a nice little clock to just remind you that, that it's not yet there. And then if we start writing an IP address, already it's telling me this is the library saying I don't have enough quads. I don't have the 4 of them. If I add another 4, it tells me that it's an IP address, but it's not a CIDR address because it's missing the subnet mask. It's missing how many bits we're going to devote to the network. So if we say we're going to devote 15, it will tell me that doesn't work. It is better for you to write it as 6.6.0.0 because the 0.6 and 0.6 are merely instances within the whole range, and the range begins at 0. But we put 15, and we said it has to be through 16. So now that is my validation kicking in. If I then turn it into a 16, not at 65, it cannot be more than 62, but if I put it to 60, now it says, okay, now you're talking. And then I can sort of describe the second time I'm describing more accurately, of course. And then if I start doing this, eventually I will exceed the 100 characters. So if I then go back, now it's valid. Once I save it, the IP access list has been updated. This is built on Vue and PHP. And here it is, right, with the description. And I can choose how many rows to display, et cetera, and I can also, of course, delete it. And if I delete it, I get the confirmation to make sure. There it is telling me that it's been removed, it's not there, and it will take 5 minutes for it to propagate. And now if I go to the apps, this turns to red because now it is restricted. So this has been an example of an approach and an implementation of an allow list in CIDR. So I think with that, I can finish. Feel free to ask me any questions. Find me on Dev on a Journey, email me there. And thank you so much for the opportunity.
Cool. Thank you, Ismael. That's really interesting stuff. There's a lot of chat going on as you're doing that talk. So try to keep up to it. Tim was mentioning there's some nice IP validation built into PHP with some examples. So that looks quite interesting. But though I assume that wouldn't check whether it's a CIDR address as well. I think that's just checking whether it's an IP or a V4 or V6 IP. But
the other element is that what I showed really was the form validation, right? Not the server side element. So because obviously I'm not going to expose the security of the app, so I haven't shared any of the PHP code at all, or any of the actual config or the environment, right? So what I mentioned earlier is that IP validation is merely one layer, and obviously the form validation is the sort of nearest, thinnest layer of everything else. But it was a good way of exemplifying the kind of things you have to take into account, not just on the front, but also throughout your application, which becomes much more complex.
Yeah, and I said I may possibly have blocked my own IP address once or twice. I was trying to set up these types of things. I wouldn't recommend doing that if you can avoid it. Does anybody in the chat have any questions that they want to post or ask? Tim says it will take any of the IP formats, but doesn't do extra specific ranges. Okay, there was a link.
Sorry, what does that mean? Does that mean, what do you mean by any of the IP formats? You mean 4 and 6, but no CIDR ranges? Is that what you mean? No, sort of no, you can't do the 1232 or whatever. It's just IP in either.
I assume so.
Is that, I think
yeah,
that's what it means.
I think it's, yeah, you can do V4 or V6, but not CIDR, I think.
And
Maybe
you can see why it would be actually
elaborate.
quite, you can see why without the CIDR block, it would be actually quite painful to do the kind of stuff that that I'm talking about.
Yeah, I remember copying and pasting a list of IP addresses and pasting them into htaccess files before now to block spam bots or something on site. So I can relate to that. There was a link to a Laravel package that was to do with IP addresses, a mutable IP address library from Laravel News. So that might be worth taking a look at later on once we're done. Okay, I assume there are no other questions, so we'll call it there. Thanks very much, Ismael.